So these are the two steps that were a little different from our first example in 8a. And that's because in 8a, we found a probability using a different method. But in general, for this hypothesis testing, we're going to need to set up a sampling distribution of proportions. Think back to Unit 6. Sampling distributions of proportions basically says that every time I take a sample from the population, let's look at 50 individuals and see what proportion are voting for this candidate, for example. If I grab 50 random people, I'll get a different sample proportion than if I grabbed 50 different random people. And the probability that that proportion equals one thing or the other is a sampling distribution. So we're trying to build a sampling distribution now around the assumption that the null hypothesis is true. That's why we had to start with those assumptions, those equations, because that's going to form our sampling distribution. So it'll give us an idea for what we expect to be true for the population if everything's working as claimed. And then we can see where our sample statistic, where our evidence, right? That's what that means. We have a claim, we have evidence, we're comparing them. We'll set up a sampling distribution, see where the evidence lies. And if the evidence is nowhere close to the assumption, then we're going to be really suspicious. Okay? And we did kind of do something a little similar with the coin tosses. We built this model based on our assumption that the coin was fair. And then we compared our evidence of 35 heads to this model. And that was really unlikely. That was far away. And that's why we were suspicious. So kind of similar. So in order to even use a sampling distribution, remember, we have to make sure the central limit theorem is satisfied. So we're going to be checking the central limit theorem, which is a little tedious, but there it is. Remember, I don't know what order I gave you these, but the order doesn't matter. Each value, each thing needs to be independent. So each of our coin tosses were independent. Each value needs to be randomly selected. Oh, I do remember. In the notes, we had these in the other order. And sometimes we can use the 10% condition to check independence. If you check back in your Unit 6 notes, you can see that. And then also we had a sample size condition. The sample had to be big enough. And specifically, we need at least 10 failures and at least 10 expected successes. We found that this way. Again, I'm not going to teach this again. Go back to Unit 6 if you're curious about these conditions. This is just a reminder. So these were the things that we did. Sampling distribution of proportions. You can use sampling distributions of means as well, but in this homework assignment, we're just going to focus on proportions. And now we could set up the sampling distribution. And yeah, we said the sampling distribution, the sample proportion under these conditions will be normally distributed with a mean of our population parameter here. That's our assumption. Right? This is from our assumption. And standard deviation, square root of PQ over N. That's the first part of step 3. We also need to calculate the test statistic. In our case, that'll be a z-score. So what is a z-score? Go back to Unit 5. Right? This is why Unit 8 is so difficult. Each problem has 5 million steps. And we've referred back to Unit 4, Unit 5, and Unit 6. Later, we're going to refer to Unit 7. So if there's any gaps in understanding, they really compound because you kind of need it all to do this unit. That's why it's hard. Okay. So how do we find a z-score? Z-score is just our value minus the mean over the standard deviation. That's how we found z-scores in Unit 5. Well, in Unit 8 now, our value, our evidence, is a sample proportion. What's the mean? The mean of our sampling distribution is p. What's the standard deviation? Standard deviation of our sampling distribution is the square root of pq over n. Not a super nice looking formula, but that's how we can find our test statistic. So this is a lot. Let's break it down. Let's do this. Let's do this for this one first, and then we'll go back to our old example and put it together. I don't want to have to turn pages that much. So let's go back to this old antacid situation. Set up the sampling distribution and calculate the test statistic. So we need independence, we need randomization, and we need sample size. So 50 people were asked if the new medication provided relief. Let's just assume. You can't always know these. So you can always ask for clarification, but let's assume that these 50 people were randomly selected. All right. The 10% condition will give us independence. Yeah. Are these 50 people selected from a group, a population of more than 500? Right? Is 50 less than 10% of the population? Yeah. We can assume independence here. If these 50 people were selected from a large enough pool that it counts as independence. What about sample size? We need to check whether we expect at least 10 successes and at least 10 failures. Well, what is our sample size? It's 50. What did we assume P to be? We assumed P was 0.7. From back here. And when you do this, you get 35. Yeah, that's bigger than 10. Good. And the expected number of failures, 50 times 0.3, could also be at least 10. Multiply that out, you get 15. So yeah, that's more than 10. Great. Central limit theorem is all satisfied here. Now we need to set up, oh gosh. I added more white space. I did not add enough white space. Every time I teach this class, I add more white space, and apparently it's never enough. All right, so that was our central limit theorem. Now we need to set up the sampling distribution. So according to this, our sample proportion should be normally distributed with a mean of p and a standard deviation of pq over n. So what was p? Again, we assumed from our null hypothesis that p was 0.7. Watch this. I can just cheat. I can give myself more space. All right. And the standard deviation, right? The standard deviation was the square root of pq over n. What is that? P is 0.7. Q is just 1 minus p. It's the leftover. And the sample size is 50. Let's type that into a calculator and see what we get. Square root of 0.7 times 0.3 all over 50. Let's use at least 4, maybe 5 significant figures. 0.06481. This is our standard deviation. So assuming the null hypothesis is true, assuming that there's no difference between the old medication and the new medication, we would expect that every time we took this sample of 50 people, we'd expect 70% relief. And that'll vary by about 6.5% on average. 68% of the time, using the empirical rule, we'd expect our sample to have be between like 76.5%, 63.5%. So this 75% would be very typical even if there was no difference, even if the new one was no different than the old medication. That's jumping ahead of ourselves a little bit, but this is our sampling distribution. What's our test statistic? Test statistic is p hat minus p. Well, I know what p is, 0.7, divided by that standard deviation, which we said was 0.06481. We just need to find what p hat is. P hat is our evidence. P hat is, maybe I should have made a note about that, right? Yeah, is from our sample. It's our evidence from our test. Well, looking at this one, what is our evidence? Our evidence were the 50 people on the new medication where 75% did. Our p hat is going to be 75%. That's going to give us our z-score. So z-score, make sure to use parentheses here. They are very important. Everything should be divided by our standard deviation. We're going to get 0.7715. Remember that z-score is how many standard deviations away from the mean you are. So we're not even one standard deviation away from the mean here. This is a very typical result. This result's not surprising. This result is very believable, even if the new medication is same as the old medication. This is our test statistic here. And that's steps 2 and 3. Again, just this one group of steps, pretty long. Let's see what it looks like in this example that we're building together. We need to check the central limit theorem. So we need randomization. We need independence. We need the sample size condition in order to even use the central limit theorem here. So we're just going to assume that these 400 people are randomly selected. We will just assume that. Do we have less than 10% of the population? Remember, that's the 10% condition from unit 1, 2, a long time ago. Yeah, I think we can say that, right? This company is testing something on 400 people. Probably a pretty big company. There's probably a lot of people that are going to be using this. They're making smartphones, okay? There's going to be more than 4,000 people. Yeah, this is less than 10% of the population. What is our sample size here? They tested on 400 people. Our sample size is going to be 400. So we need n times p to be bigger than or equal to 10. P we're assuming to be 96%. You multiply this all out, and you get something. 400 times 0.96. I think I know what it is. 384. That was my guess. That is at least 10. That's great. And we need to expect at least 10 failures as well. Well, 400 times 0.96. Sorry, the failure is 0.044%. That's going to be 16 people. It's barely over 10, but it is over 10. Great, so we can use the central limit theorem. Now let's set up the sampling distribution and do our test statistic. So we know p hat is normally distributed with a mean of p, standard deviation square root of pq over n. We just fill in the blanks now. P. We said we're assuming that P is 0.96. Now just type in the calculations to find out what our standard deviation should be. Square root of P times Q. Remember, Q is just 1 minus P. All over N. N is how many? Press enter. 0.009798. Make sure to include at least 4 significant figures in these. That's our sampling distribution. Good. Let's find our test statistic. It'll be P hat minus P all over the square root of PQ over N. What was our sample here? Our sample proportion. Well, we tested it on 400. It was successful on 376. What proportion is that? P hat is just 376 over 400. This is the proportion that worked for us when we collected our evidence. 376 over 400. Going to be 0.94. So in our situation, we had 94%. Remember what we're doing here. We're trying to check whether we failed. We're trying to check whether we're less than 96%. So again, our sample definitely was less than 94%. Or it definitely was less than 96%. Our sample was 94% success. But was that just due to randomness? Or do our instructions just actually suck? That's what we're really asking here. Is this strong evidence that we're failing? I know we failed, but did we just fail because randomness and unluckiness? Or did we fail because we're really less than 96%? All right, so P we're assuming to be 96%. And our standard deviation was at 0.009798. Type this into a calculator and see what we get. Make sure to use parentheses. And woo, negative 2.0412. Remember what your test statistic means. It's a z-score. That means we're 2 standard deviations below the mean. That is not likely, right? Remember past 2 standard deviations? We usually think of that as an outlier. So if everything's going according to plan, if we are meeting our goal of 96%, there's a pretty unlikely to have something this low of 94%. We'll talk about how likely that is in the next video. Okay. So there was another example. I'm not going to go through it. We already went through 2 examples. But let me know if you have questions about what letter B would look like. Anyway, we're almost done. We get the last steps in the last video and then tons more practice for you. Hang in there. You got it. These are long problems, lots of steps, but we are doing it.